The rules of differentiation are really the foundation for finding antiderivatives. So here we differentiate x to the power of n with respect to x, and by the power rule we put down the exponent and then subtract 1 from the exponent. And here we've also included a constant which disappears when you differentiate. Now to go in the opposite direction, what we do is separate dx and then integrate both sides. So effectively the integral of the differential gives us back x to the n plus c, which is equal to the integral of the expression on the right. And we call this an indefinite integral because it doesn't have limits of integration, but finding the antiderivative is similar for definite and indefinite integrals. So in general, if we have an integral of x to the power of n with respect to x, we add 1 to the exponent and divide by the resulting exponent and add a constant of integration, where n is not equal to minus 1, or we get to divide by 0. And this here is the power rule for integration. We can also apply the rules for differentiating elementary functions to give us a clue on how to integrate them. So using this one as a guide, we can obtain the integral of sine of a constant by x. So when we differentiated, we multiplied by k and negated the result. So when we integrate, we divide by k and negate the result. And where we have an indefinite integral, we add a constant of integration. Now we can evaluate the integral of cosine a constant by x in a similar way. So here when we differentiate, we don't have a negative sign. So we simply divide by k and multiply by sine kx. And the other integrals are obtained in much the same way. We can also use the derivatives of the other trig functions as a guide to obtain their antiderivatives. So differentiating tan of a constant multiplied by x, we multiply a constant by sec squared kx. So that tells us how to integrate sec squared kx. So we effectively divide by k and multiply by tan kx. And where we have an indefinite integral, we add a constant of integration. And a similar result can be obtained by integrating cosec squared kx. So when we differentiated the cotangent, we multiplied cosec squared kx by a negative constant. So to obtain the antiderivative, we have minus 1 on k by the cotangent of kx plus a constant of integration. And similarly, if we want to integrate sec kx tan kx, so we simply just divide by the constant k and multiply by sec kx and add a constant of integration. And in a similar way, we can integrate cosec kx by the cotangent of kx. We can also use the derivatives of inverse trig functions, which were derived earlier, to obtain the antiderivatives of reciprocals of radicals and reciprocals of polynomials. So integrating 1 over the square root of 1 minus x squared with respect to x is basically just going backwards to arcsine. And where we have an indefinite integral, we add a constant of integration. And sometimes this integral may not be perfectly aligned with 1 over the square root of 1 minus x squared. So we'll introduce other integration techniques later on, such as completing the square, to generally get the integral in this form. And the same thing applies to this integral, for example. So this will directly give you the arctan of x plus a constant of integration. But you may get 2 on 2 plus x squared, and so on, and you might need to do a bit of algebra to get the integral in this form. And we'll have some practice with that. We can also use the derivatives of logarithms and exponential functions to obtain the antiderivatives. So remember when y equals log base a of x, we took a to the power of both sides, and then we took the natural log of both sides and divided by the natural log of a. So if we wanted to integrate 1 over x by the natural log of a, then you can take the constant outside the integral, so this will give you the natural log of x on the natural log of a plus a constant of integration. And as we can see, that's equal to y, which is log base a of x. So effectively this expression is the same as this one over here. And we can also use this derivative to integrate exponential functions with a base a. So what we do is just divide through by the natural log of a and multiply by a to the x and add a constant of integration. Let's evaluate the following accumulation function. So if we evaluate this integral using the first fundamental theorem of calculus, we get t cubed evaluated from 1 to x, and therefore g of x is equal to x cubed minus 1. So if we plot this function here, it looks something like this. So we're integrating from 1 to x, and the function just accumulates as x moves to the right. So at x equals 4, what we get is 64 minus 1, which is 63. Let's evaluate the accumulation function at x equals pi and 2 pi. So if we integrate this, what we get is minus cosine t, evaluated from 0 to x. And that's thereby equal to minus cosine x minus cosine 0, which is plus 1. So note that the sine function can be plotted like this. So it's equal to 1 at pi on 2 and minus 1 at 3 pi on 2. And the function is accumulating the area from x equals 0 to some x over here. So at x equals pi, we have f of pi is equal to minus 1 plus 1, which is 2. And then to 2 pi, we get an accumulation of 0, because we have a positive area and an equal negative area here which cancel out. Let's evaluate the accumulation function at x equals 3 pi on 2. So we get sine t evaluated from pi to x. So that gives g of x is equal to sine x minus sine pi, which is 0. So if we plot cosine x, it looks something like this. So at x equals pi on 2, cosine is 0, and at 3 pi on 2, cosine is 0. And it's equal to minus 1 at pi. So since the function is accumulating from x equals pi to some x over here, well, what we get is g of 3 pi on 2 is equal to minus 1, because the function is evaluated using this area over here, from pi to 3 pi on 2. Let's evaluate this integral. So it looks like a simple application of the power rule, because this term here is x to the minus a half. So therefore, we get 3 by x to the 4 on 4, plus x to the 1/2 on 1/2, which is 2x to the half, and then plus 5x, and plus the constant of integration. Let's evaluate this integral. So one thing you may recognize is the derivative of cosec a constant by x is equal to minus k cosec kx by the cotangent of kx. So if we divide through by minus k and then integrate both sides, where this here is the integrand, well, what we get is minus 1 on k. So this time we have minus 1 on pi on 4, which is 4 on pi, and cosec pi on 4x, plus the constant of integration.